viewers, welcome to today's lecture on transmission of analog signal. In the last two lectures, we have discussed about the transmission of digital signal. There we have seen how analog and digital data can be encoded into a digital signal form and which can be transmitted through the transmission media, various types of transmission media. And we have seen how the encoding is done so that the signal matches with the bandwidth of the signal matches with the bandwidth of the transmission media, so that it passes with less attenuation, less distortion, and also it provides you necessary signaling for synchronization and other purposes. Error detection and also synchronization is possible. Now we shall focus on the transmission of analog signal, and in this lecture we shall cover these topics. First we shall discuss why modulation. It is essential an introduction to this particular lecture, the need for modulation. Then we shall consider various modulation techniques, and in this particular lecture we shall primarily focus on amplitude modulation. So, we shall introduce to you the basic concepts of amplitude modulation. Then you will see there is a concept called modulation index which will be introduced to you. Then frequency spectrum of AM signal we shall consider. Average power of different frequency components. Whenever a signal is amplitude modulated, it generates different frequency components, and what is the average power of different frequency components, that we shall consider. Then we shall consider some special situations like single sideband SSB and DSB SC, double sideband suppressed carrier transmission. Finally, we shall discuss about the recovery of baseband signal. After attending this lecture, the students will be able to explain the need for modulation. They will be able to distinguish between modulation techniques. They will be able to identify the key features of amplitude modulation. Then they will be able to explain the advantages of SSB and DSB-SC transmission. Finally, they will be able to explain how the baseband signal can be recovered from the received signal. So, this diagram gives you the basic scheme of analog data to analog signal. Here, as you can see, we have used one analog data as an input to the analog to digital, analog to analog conversion system. Here, apart from applying this analog data, another auxiliary signal which is known as usually that is a sinusoidal signal, which is applied to this analog to analog converter, and that is known as carrier. And this carrier is essentially a sinusoidal signal, and as we shall see, one of the important parameters of this carrier, as you know, a particular analog signal, whenever it is a sinusoidal, there are three important parameters by which the signal can be characterized, that is the amplitude, phase and frequency. Either one of them individually or a combination of them are modified to generate a signal which is known as modulated signal. So, here is your modulated signal. Modulated signal, and this process of applying a signal to be modulated, so this is known as modulating signal. So, modulating signal and carrier, these two are applied to the converter, the modulator, and this process of conversion from analog data to analog signal, which involves manipulation of one or more of the parameters of the carrier, that is amplitude, frequency or phase that characterizes the analog signal. This process is known as modulation. So, this process is known as modulation. And you may be asking why modulation is necessary. You will see that when we do modulation, one important operation that is being performed on the signal, which is known as frequency translation. What it does? It translates the signal from one region of frequency domain to another region. It is like this. Suppose this is the representation of the signal in frequency domain. So, here you have got your f, and obviously in this you have got the amplitude. Now, suppose you have a signal with frequency range, say f1 and f2. So, this is the range of frequency, and we can say that this is the this is how you can represent it. You have frequency components from f1 to f2. Now, by modulation, these two frequencies, this signal can be translated to another frequency range, say f1 dash to f2 dash. So, to this. So, it can be translated to another frequency range, and usually this frequency range f1 dash or f2 dash is much higher than f1 and f2. So, this is how this can be translated. However, the information content of the translated signal is such that the original signal can be recovered from it. Now, you may be asking, what is the benefit of this? The benefit of this is, one important benefit of this is that you will be able to use an antenna of practical size. So, whenever you do translation, say baseband signal to higher frequency, which can be transmitted through a band pass channel using an antenna of smaller size. Suppose you are trying to send a 1 kilohertz signal, and what is the wavelength for this? If this is the frequency, what is the lambda value? As you know, the wavelength will be 300,000 meter. We have already discussed about it. Now, whenever you are trying to send a frequency of 1 kilohertz, the wavelength is 300,000 meter, and obviously the antenna has to be comparable to this size. Obviously, an antenna of this size, 300,000 meter, is impractical. You cannot do it. However, if you translate it to a frequency, say translate it to, let us assume you translate it to say 10 megahertz. Whenever you translate it to 10 megahertz, this will correspond to a lambda that is equal to only 30 meter. Obviously, it is quite possible to have an antenna of 30 meter. So, after translating this to a higher frequency, then you can have an antenna of smaller size, and then this signal, this modulated signal, can be transmitted very easily using smaller size antenna. And of course, at the other end, after receiving it, you have to do demodulation, which we shall discuss later. So, this is the first benefit of modulation. You will be able to have an antenna of practical size. What are the other benefits? Another important benefit of this modulation is narrow banding. Suppose you are trying to send a frequency range of, say high fidelity audio frequency range, which has frequency range of 20 hertz to 20 kilohertz. So, you can say hi-fi audio. Obviously, you are sending music and other thing. So, you see the ratio of the highest frequency to lowest frequency is quite high. That means, highest frequency is 20 kilohertz and the lowest frequency is 20 hertz. The ratio between highest frequency to lowest frequency is 1000. And obviously, if you design an antenna for this frequency, then it is not at all suitable for this frequency. or if you design an antenna for highest frequency, then it will not be suitable for transmission for lowest frequency. So, you see, a single antenna will not be able to cover or able to transmit both the signals effectively and efficiently. Now, suppose you modulate it using 1 megahertz signal. The carrier frequency is 1 megahertz. Now, this frequency is translated to say 1 megahertz, that is your 10 to the power 6 plus 20 hertz, and this one becomes 20 into 10 to the power 3 plus 10 to the power 6 megahertz, 6 hertz. So, you see, now you take the ratio, if you take the ratio between the two, the ratio will be only 1.002. That means, if you design an antenna for this frequency, highest frequency, that will be able to send the lowest frequency very easily, because as you can see, the ratio between the highest and lowest frequency is only 1.002. In other words, a single antenna will be able to transmit both the frequencies efficiently and effectively. That this process is essentially narrow banding. You see, we are converting a wide band signal, wide band not in terms of absolute values. You can see here 20 hertz to 20 kilohertz, their frequency is not really very high frequencies. However, this is, you may consider it wide band in terms of the ratio of the highest frequency to lowest frequency. Now, it is translated into a frequency of very narrow band, and narrow band having the ratio of highest to lowest is only 1.002. So, you see, this allows you to transmit very effectively by using suitable antenna. So, this narrow banding is another benefit of this modulation. Third benefit is multiplexing. As you have seen, whenever you do the multiplexing, suppose here is your signal, original signal having bandwidth say 0 to, let us assume this is f1 to f2, f1 is very close to 0. This signal is usually called baseband signal. Now, you translate to a frequency say from f1 dash to f2 dash. Now, this is converted into a band pass signal, which can be transmitted through a band pass channel. Now, another frequency of the same range can be translated to frequencies such as f1 double dash to f2 double dash. Now, both of them can be sent through the same channel. As you can see here, since the you can separate them with the help of band pass filter at the receiving end. In other words, this allows you to send both these two separate signals simultaneously through a transmission media. This process is known as multiplexing, and this allows you frequency division multiplexing. As you can see here, the frequency range or the bandwidth available is divided, say this is one part, this is another part. In this way, you can divide it into a number of frequency range which can be sent through the transmission media. Then at the other end, the receivers will be able to separate them by suitable filtering. So, this is another benefit of this modulation, that is multiplexing. It allows you multiplexing. Here are the various modulation techniques that is possible. As I told, you will be able to modify one of the three parameters: amplitude, frequency and phase. Whenever you vary the amplitude, we get amplitude modulation, that means amplitude of the carrier. Second alternative is known as angle modulation, where you are modifying the frequency, that means the frequency of the carrier is modified based on the signal to be sent or modulating signal, or it can be phase modulation. These two together are known as angle modulation. In this lecture, we shall primarily focus on amplitude modulation. So, here you see we are giving an example of a signal. This is a baseband signal of low frequency. In this case it is a sinusoidal signal, and this is your carrier. And here as you can see, the amplitude of this carrier has been modified with the help of this baseband signal. That means now here the amplitude is maximum. So, you have got amplitude, maximum amplitude, here it is minimum. So, minimum amplitude. So, we get a carrier frequency with time varying amplitude. This is known as modulated signal. So, here you get modulated signal, and this is the how it is done we shall discuss. Let the waveform is represented by this equation EMT is equal to capital EM cos twice pi FMT. Here you see we are considering that the modulating waveform is a sinusoidal wave with frequency FM having maximum amplitude EM, and the carrier signal is represented by ECT equal to capital EC cos twice by FC plus phi C. Here you see the maximum amplitude is EC, it has got frequency FC and a phase difference phi C. Then the equation of the modulated signal can be given by ST, which is equal to capital EC plus capital EM cos 2 pi FMT into cos 2 pi FCT. So, this is the signal which is generated after modulation, and there is an important parameter called modulation index, which is represented by M. M is given by Emax minus Emin by Emax plus Emin, that is equal to if you look at this diagram, here you see this is your Emin and this is your Emax of the modulated signal. Now, that Emax and Emin, if Emax and Emin are the maximum and minimum values, then modulation index M is equal to Emax minus Emin by Emax plus Emin. Then as you can see here, Emax is equal to EC plus EM. That means here as you can see, this maximum amplitude will be equal to Emax, which is equal to EM plus EC. On the other hand, this minimum amplitude will be equal to Emin, which is equal to EM minus EC. Then M that we get is equal to M is equal to modulation index is equal to Emin by Emax. That is given by Emax minus Emin by Emax plus Emin, which is equal to EM by EC. That means we get in this case we get M is equal to EM by EC. In this particular case, EM is equal to given by the amplitude, maximum amplitude of the modulating signal, and EC is the maximum amplitude of the modulated signal. Now, this kind of waveform you get whenever the value of M is equal to less than 1. That means the amplitude of the modulating signal, maximum amplitude of the modulating signal is less than the maximum amplitude of the carrier. Then we get a waveform like this. Now, let us see what happens whenever you increase the modulation index. As you increase the modulation index or the value of M, as you can see here, the value of EM has been increased compared to the previous diagram. So, here what has been done, EM has been made equal to EC. So, in that case what is happening, you are getting the value of M is equal to 1, because M is equal to EM by EC. So, for EM M is equal to 1, as you can see in this case since this signal amplitude of this and the amplitude of this is same, then the difference is 0 and the maximum value is 2 EC. So, it varies from 0 to 2 AC. So, in that case we get the maximum modulation, that means this is the maximum permissible modulation possible, because as we shall see in the next slide, when you get m is equal to greater than 1, here the value of EM has been made greater than EC. So, when EM is greater than EC, then value of m is greater than 1, and in such a case we get a waveform like this, and it can be shown that whenever you have m is greater than 1, then you do not get it is not possible to recover the signal at the other end. That means, recovery of the signal will not be possible whenever the modulation index is greater than 1. Let us now look at the frequency spectrum of the modulated signal. First, let us consider whenever we are modulating by using a sinusoidal AM. That means, the modulating signal is a sinusoidal signal, and in that case the modulated signal will be equal to ST equal to EC into 1 plus m cos twice pi FMT into cos twice pi FCT, which can be extended into which can be expanded to EC cos twice pi FCT plus m EC cos twice pi FMT cos twice pi FCT. This particular term can be expanded, can be represented by this form. So, m by 2 EC cos twice pi FC minus FMT plus m by 2 EC cos twice pi FC plus FMT. So, we now notice that there are 3 frequency components. One frequency component is FC, another frequency component is FC minus FM, and third frequency component is FC plus FM. So, after modulating a sinusoidal carrier with the help of a sinusoidal modulating signal, we get 3 frequency components and their respective amplitudes are shown in this diagram. Here we see we get a carrier of peak amplitude EC, we get lower sideband, this is known as lower sideband. Lower sideband, this is your carrier and this is your upper sideband or higher sideband. So, this higher sideband has an amplitude MC by 2 EC. So, we see M by 2 EC, EC and M by 2 EC, these are the 3 signals having amplitude, different amplitudes. So, EC cos twice pi FCT and M by 2 EC cos twice pi FC minus FMT, and so these are the 3 frequency components. Obviously, these amplitudes are dependent on the, since M is, as you know, the ratio of EM by EC, essentially this will be equal to EM by 2 and this will be also will be equal to EM by 2. That means, the sideband frequencies will have amplitude that is equal to EM by 2, because M by 2 into EC will be equal to, as you know, M is equal to EM by EC. So, EC will cancel out, will give you EM by 2. That means, the amplitude of the side frequencies will be equal to EM by 2, which is dependent on the amplitude of the modulating signal. Now, what is the effect of this? Let us take with the help of an example. Suppose here a carrier of 1 megahertz and peak value 10 volt is modulated by a 5 kilohertz sine wave having amplitude, maximum amplitude 6 volt. Determine the modulation index and frequency spectrum. So, in this case, what is the value of M? Value of M will be equal to EM is 6 and EC is equal to 10. So, this is 6 by 10, that is 0.6. Obviously, this is less than 1. That is very good. We get good quality signal which can be recovered. That means, original signal can be recovered from the modulated signal that is being received. And what will be the range of frequencies? So, what will be the range of frequencies? 1 megahertz minus, that means 10 to the power 6 minus 5 kilohertz, 5 into 10 to the power 3, 2 it will be 10 to the power 6 plus 5 into 10 to the power 3. So, you see this will be the range of frequencies, and bandwidth is equal to is difference of the two, that means is equal to 10 into 10 to the power 3 hertz, or the bandwidth is 10 kilohertz. So, you see that bandwidth is not very high, twice that of the modulating signal. So, this is shown in this particular diagram. So, here we see the modulation index as we calculated 0.6, and the side frequencies are 995 kilohertz, and so since we are modulating with it sinusoidal, the other frequencies are not there, we shall get 3 frequency components 995 kilohertz, 1000 kilohertz and 1005 kilohertz. So, these are the frequencies, and you can see here we get the three amplitudes of the frequency components. The carrier will have 10 volt, the side bands will have 3 volt. So, this is the that frequency domain representation of the signal of the modulated signal. Obviously, the time domain representation we have already seen, that time domain representation will be somewhat like this, and on the other hand the frequency domain representation, as you can see here, will have like this, that means three spectral components. So, now let us consider the bandwidth whenever the modulating signal is not a simple sinusoidal wave. We are now modulating the signal with the help of audio signal, and in that case the audio signal has a bandwidth of Bm. So, we can see from almost 0 to Bm, that is the bandwidth of the audio signal. Now, the modulated signal will have bandwidth starting from Fc minus Bm. So, here is your Fc minus Bm to Fc plus Bm, and as you can see bandwidth is equal to 2 Bm, that is the bandwidth of the signal. So, the bandwidth of the modulated signal is 2 Bm as it is written there. So, we see that after modulating a carrier of frequency Fc, we get frequency translated signal having bandwidth twice the bandwidth of the modulated signal, modulating signal. So, modulating signal has bandwidth Bm, so we get twice the bandwidth, and of course, the amplitudes of different frequencies will be based on the modulation index as you have seen. Now, how much power will be associated for transmitting this signal? It is very important to know, to understand the power required for transmission of the analog signal. So, as you have seen, there are 3 different frequency components. So, each of the frequency components will require power for transmitting through the antenna. So, let us assume that the power is developed across a resistor of value R, then for the carrier the average power is equal to EC square by 2R, and the sideband frequencies this is for sinusoidal wave. So, for any one of the sinusoidal frequency, that will be equal to this is voltage m is C by 2. So, that is V square by 2R. So, here it is Pc into m square by 4. So, since there will be two side bands to calculate the total average power, you have to add the power required for transmission of the carrier and also the power required for transmission of 2 side bands. So, if you add up, you get the total power required for transmission, that is equal to Pc into 1 plus m square by 2. That is the total power required for transmission. Now, one very interesting observation from this is that maximum power is required for transmission of the carrier. We have seen in the previous diagram, you can see here it is EC square by 2R, and about as you can see, depending on the modulation index, the sideband power, as you know, usually m is less than equal to 1. So, this value will be always less than 1/4. That means you are using 1/4 of the power, less than 1/4 of the power to transmit one of the sidebands. That means half of the power is transmitted to send the two sidebands, less than half, and half of the power you are using to transmit the carrier signal. Now, for recovery purpose, do you really need all the three frequency components? It has been found that we can recover the original signal even when the carrier is not transmitted. That means, even if we have two sidebands, then we can recover. So, that has led to what is known as double sideband with suppressed carrier modulation. So, transmission is possible by suppressing the carrier and by sending only the two sidebands. Another alternative is you can send one of the two sidebands. So, the original signal can be theoretically recovered. There are some practical aspects that we shall consider later. However, it is possible to recover the modulating signal from one of the two sidebands. So, if we can send only one of the two sidebands and can recover the original signal, that is modulating signal, that means we shall be able to perform transmission with minimum power. The power required for transmission, power required to drive the antenna will be much less. So, this has led to two different types of modulation. One is double sideband suppressed carrier modulation. So, this utilizes the transmitted power more efficiently than double sideband AM transmission. The normal transmission is known as DSB AM, where we are transmitting both the sidebands as well as the carrier. So, what has been done, this is your normal DSB transmission, double sideband transmission. Now, the carrier has been removed, and as we have seen, as you can see here, we have got only two sidebands. So, this is your DSB-SC, double sideband with suppressed carrier transmission. So, we see the carrier is not present. So, to transmit this signal will require less than half the power than that is possible by using double sideband transmission. So, this is the primary advantage of the DSB-SC modulation. However, it has some disadvantage in recovering the signal that we shall discuss later. As we have mentioned, the another alternative is to use single sideband modulation. So, in single sideband modulation, as you can see, you can send either the upper sideband or the lower sideband. So, in this particular case, as we have seen, the power required for transmission is not only 1/4, less than 1/4 I would say. If modulation index is less than 1, obviously the power requirement will be less than 1/4, and not only you will be able to transmit with lesser power, the bandwidth requirement is also reduced. Here you see, for upper sideband, bandwidth is FC to FC plus FM, and for lower sideband it is FC minus FM to FC. So, whenever you have bandwidth crunch, you have to multiplex many signals, then single sideband is the solution. So, as you can see, the modulated signal can have only bandwidth of BM, and as a consequence this is very efficient in terms of bandwidth as well as in terms of energy that is required for transmission. Now, let us focus on the recovery of the baseband signal. How do you recover the baseband signal at the receiving end? Obviously, we are transmitting signal with the sole purpose of getting back the modulating signal. That means, if you are sending audio signal, then at the other end we would like to get back the audio signal undistorted in its original form. And how that can be done? One approach is by multiplying the signal second time. As you can see, let the baseband signal is empty, and after multiplication with the carrier, the signal is now get converted to empty cos twice pi cos WCT. WC is twice pi FCT. So, we see this is the modulated signal. Empty cos WCT is the modulated signal that is being transmitted. Now, we multiply this with the help of using the carrier signal. So, if we multiply the original signal, that is your modulating signal, second time with the carrier signals. First time we have multiplied with the carrier signal to get the modulated signal. Now, you are multiplying second time. Let us see the effect. We get empty cos square WCT, which can be expanded to empty half plus half cos WC2 half cos 2 WCT. So, we find that it has got two components. One is empty by 2, another is half empty cos 2 WCT. So, we observe that the baseband signal has reappeared here. However, not only the bandpass signal, the baseband signal has reappeared, you have got two other frequency components like 2fc minus fm and 2fc plus fm. If you expand this half empty cos 2 WCT, you will get two frequency components. These are 2fc minus fm and 2fc minus plus fm. However, normally fc is much greater than fm. As a consequence, these spectral components 2fc minus fm to 2fc plus fm can be very easily removed by using low pass filter. That means, if you use low pass filtering, then you can get back only the baseband signal. So, this approach is known as synchronous detection. That means, whenever you multiply the modulated signal second time by using the carrier, you get back the baseband signal after filtering out the other high frequencies such as 2fc minus fm and 2fc plus fm, and this process is known as synchronous detection. Now, there is one important limitation of this synchronous detection. The important limitation is the signal cos 2 WFC has to be precisely synchronous. So, the synchronous detection approach is straightforward, but it has the disadvantage that whenever you do the multiplication, then that carrier signal which you are using for multiplying second time has to be precisely synchronous. That means, there should not be any phase difference. If there is any phase difference, then you will see that after multiplication the signal that you get will not be the baseband signal. Question is, how do you get the synchronous signal? So, you have to use costly hardware to generate the precisely synchronous carrier signal at the receiving end. At the receiving end, that is why it is better to have normal double sideband signal, double sideband modulated signal, So, if you receive the carrier, that carrier can be used to regenerate or generate a synchronous carrier, which can be multiplied to get back the baseband signal. However, if you do not send the signal, if you use that DSBSC, then it will be very difficult to generate the second carrier at the receiving end, synchronous carrier at the receiving end. So, this is a very difficult process. On the other hand, if we use that original DSM signal, it can be recovered very easily by a simple circuit like this. We can use one diode, a capacitor and a resistor. This can be grounded. So, across this you can get back. So, here you apply the modulated signal, here you will get back the baseband signal. This type of simple circuit can be used if we use DSM signal. That means, there is no need for synchronous detection. You can use this kind of simple circuit as it is shown here. A diode, resistor and capacitor combination can be used to get back the original signal. As you can see here, the value of R and C can be chosen in such a way that it will follow the carrier. That means, you will get this particular curve, which is essentially the baseband signal. So, which will, and since this frequency is very high, Fc is very high, then Fm, this will be quite smooth and it will remove, you will get a that baseband signal recovered here by using this kind of simple circuit. So, this is known as detection with the help of a diode, and this is commonly used in many situations. Of course, the modulated signal received at the receiving end is greatly attenuated. As you know that the signal is passing through a long distance, and the attenuation is proportional to 1 by distance square, and as a result, if the receiver is at a long distance, the signal will be highly attenuated. Not only that, the atmosphere is always generating some noise when there is lightning, spark, and there are various other atmospheric disturbances. So, at the receiving end, the signal to noise ratio is very poor, and also the signal level is very low. Moreover, there may be many other channels adjacent to the signal. That means, you will be using some kind of frequency division multiplexing. So, a number of channels may be transmitted, and they can be very close, side by side. So, in such cases, the recovering the signal may be little difficult. So, whenever the signal is highly attenuated and you have got many channels adjacent to it, the signal has to be amplified before you can do detection, and the noises are to be removed by suitable filtering. And for this purpose, one approach that is commonly followed is known as super heterodyne approach. Let me explain the super heterodyne approach with the help of the block diagram that is commonly used. Here you see you have got an antenna. This is the receiver, complete receiver circuit. Here is your antenna where you are receiving signal of the order of maybe microvolt or less. Then there is an RF amplifier. RF amplifier is essentially amplifying the carrier signal. So, this is tuned to the carrier frequency. So, here there is a tuned circuit, and that is amplifying the RF carrier, tuned amplifier. Then in the super heterodyne technique, what you do, you use a local oscillator having frequency FOSC. This local oscillator frequency is greater than the FRF, that it is greater than the RF frequency. So, this local oscillator frequency is mixed with the amplified carrier signal, amplified RF signal, and whenever you do that, as you know, the signal that we have received is shown here, which has the carrier frequency and 2 side bands. Now, whenever you do the mixing with the help of a local oscillator which has higher frequency than FRF, that is why it is called super heterodyne. If this oscillator frequency is less than the RF, then it is not super heterodyne, and whenever you multiply mix with FSC and this modulated carrier, you will get frequency spectrum like this. You will get intermediate frequencies equal to FOSC minus FC and FOSC plus FC. That means you get frequency FIF is equal to FOSC minus FC and also FOSC plus FC. These two will be there. Now, what you do, you simply filter that FIF, that intermediate frequency is filtered with the help of intermediate frequency amplifier. So, intermediate frequency amplifier not only it filters out this frequency component, it also does it also amplifies it. So, it does the filtering and amplification together, and then it is applied to a detector. So, here it is applied to a detector. That detector will generate the baseband signal. So, the baseband signal, and of course, that RF there will be some the radio frequency noises which can be filtered out with the help of low pass filter as shown here. Then you will be applying to a audio amplifier. So, after detection and low pass filtering, you will get back the audio signal as it is shown here. So, which is amplified and applied to a loudspeaker. This is the typical AM receiver that we use in our houses. This is a common household item. So, this super heterodyne approach provides us a number of benefits. First of all, it is used to improve adjacent channel selection. It provides necessary gain, because as you can see, amplification is done at different stages. So, here it can be microvolt, then it is here millivolt. Before, whenever you do the detection, here it can be of the order of volt. So, microvolt to volt, a gain of about 1000 is performed as it goes from RF to audio. Then it provides you better signal to noise ratio, because that's because of the filtering and also the tune filtering, that only the carrier frequency is received. So, the signal noise is rejected and we get the good quality signal. And this is the commonly used technique of popular AM receivers. So, we have discussed the amplitude modulation technique, we have discussed what is modulation index, the frequency spectrum, the power required for transmission, and we have also discussed how the signal can be recovered. And in the next lecture, we shall discuss about the angle modulation, and as I have mentioned, it has got 2 different versions: frequency modulation and phase modulation. And this is how it will look like. You see, there will be no change in amplitude, but frequency is modulated. Here are the review questions based on this lecture. First one is, why are the benefits of, I think it will be, what are the benefits of analog modulation techniques? Second question is, what are the possible analog to analog modulation techniques? Third question is, what is the bandwidth requirement of amplitude modulated signal. Fourth question is, what is the single sideband transmission? What is single sideband transmission? What are the advantages of SSM transmission, single sideband transmission? Fifth question is, why synchronous detection is not commonly used to recover the baseband signal? Now it is time to give the answers of the previous lecture. First question was, why B8ZS coding is preferred over Manchester coding for long distance communication? As you know, the B8ZS encoding is preferred over Manchester encoding because B8ZS encoding requires lesser bandwidth. Bandwidth, as you have seen, is equal to the bandwidth of the signal, baseband signal. But the Manchester encoding has bandwidth about twice the almost twice the baseband signal. So we see that B8ZS has lesser bandwidth, which is useful. That is why it is preferred for long distance communication. Second question was, why is it necessary to limit the band of a signal, bandwidth of a signal, here also bandwidth of a signal, before performing sampling? Answer is, it is necessary to limit the bandwidth of a signal before sampling so that the basic requirement of sampling theorem, that is the sampling rate should be twice or more than twice the maximum frequency component of the signal, is satisfied. This is known as Nyquist rate, as I have already discussed. If it is violated, original signal cannot be recovered from the sampled signal. So, it will suffer some kind of distortion, which is known as aliasing error. Third question was, distinguish between PAM and PCM signals. Answer is, in order to recover or in order to convert analog data to digital signal, initially sampling is done on the analog data by using sample and hold circuit. The output of the sample and hold circuit is known as PAM signal. The PAM signal is then converted to PCM signal. So, PAM is essentially an intermediate step to get the PCM signal. After you have got the PCM signal, a analog to digital converter is used to quantize the signal, then you use an encoder to generate the PCM signal. Line encoding is done. So, you see PAM is essentially an intermediate step for generating PCM signal. Fourth question was, what is quantization error? How can it be reduced? Answer is, to convert analog signal to digital signal, the analog signal is first sampled and each of these analog samples must be assigned a binary code. In other words, each sample is approximated by being quantized into some binary codes, as you have already seen. As the quantized values are only approximations, it is impossible to recover the original signal exactly, and this leads to quantization error. And quantization error can be minimized by using nonlinear encoding, as we have already discussed. Fifth question was, explain how in what situation DPCM, that is differential PCM, performs better than PCM. The answer is, DPCM performs better when the input is slowly changing, as in case of voice signal. As you have already seen, whenever the signal is slowly changing, then the differential PCM will require very small number of bits, and as we know, the delta modulation is the extreme case where you require only one bit. So, however, if the signal is not slowly changing, then this approach cannot be used. So, only when the signal is slowly changing, this can be used. DPCM has better performance than PCM. So, with this we come to the end of today's lecture. Thank you. Hello and welcome to today's lecture on analog transmission. This is the second lecture on this topic, and in this lecture we shall cover these following points. I shall give a brief introduction what we have discussed in the last lecture on the same topic. After that, I shall introduce to you the basic concepts of angle modulation, and essentially we will see angle modulation involves two types of modulation, frequency modulation and phase modulation. Then I shall discuss the relationship between frequency modulation and phase modulation. Then we shall consider the bandwidth and power required for FM and PM transmission. Then we shall switch to a different topic, basic concepts of digital data to digital signal conversion, where there will be three different types. First one will be amplitude shift keying, and we shall consider in detail the various issues related to amplitude shift keying, particularly frequency spectrum of ASK signal, the power requirement for transmission of ASK signal, and also we shall discuss about the frequency and phase shift keying. Then we shall end our lecture with applications of different types of conversion technique, digital signal conversion techniques. And on completion of this lecture, the students will be able to explain the basic concepts of angle modulation. They will be able to distinguish between the FM and PM, particularly their interrelationship. Then explain the basic concepts of digital data to digital signal conversion. So here we see we have got the digital data in terms of ones and zeros, which is converted into some signal. Then we get the analog signal. So you see here, according to this data, this is some modulation has been done to get analog signal. Here you see it is analog signal. This corresponds to logic bit 1, this corresponds to 0, this corresponds to 1, this corresponds to 0, this corresponds to 2 ones, then 2 zeros. So this corresponds to the data that we are transmitting. But instead of sending 1, we are sending an analog signal. For 0, you are not sending anything like that. And this is your analog signal. And there are three distinct types of digital to analog modulation technique. One is known as amplitude shift keying, phase shift keying, and frequency shift keying and phase shift keying. And as we shall see, amplitude shift keying and phase shift keying can be combined to have another type of modulation technique, which is known as quadrature amplitude modulation, QAM. So we shall discuss all these four types of modulations, ASK, FSK, PSK and QAM in this lecture. So review questions are: number 1, which modulation technique is used in optical communication? Second question is, what are the 3 modulation techniques possible in modems?